Thank you, Tarek. That was the biggest ego boost that I have received in recent times, because working day to day in the company is not anywhere like that. You are in touch with reality a lot more. Thank you for having me here. You can hear me all right, right? Okay. Okay, so I'm going to talk about building intelligent machines that work like the human brain. In fact, I would contend that intelligence is one of the most misunderstood topics that exists. We don't really understand what intelligence is. In fact, if there is something that is more misunderstood than intelligence, that is human-level intelligence. Even that is misunderstood and often used in inappropriate contexts. I hope I will get to explain this throughout the talk. So, to me, intelligence, a succinct definition for intelligence would be the ability to model the world and to act on it, and to act purposefully on it. Remember, these two words are important: model and act. In fact, let me give you a demonstration of that. When I arrived here, I saw this contraption. I have never seen that before. I haven't gotten into it. I am thinking about it. And what is going through my mind? I am thinking about the consequences. How if I get in, what will happen? If it gets stuck, what will happen? How does it go at the top? If I stay in the machine, would I go upside down? How does it switch over to the other side? I have no idea. But I am building. I'm thinking. I'm building a model of it. I did not need any training, examples from this. I just watched this, and I'm going through these questions, and I'm very interested in reading the user manual of it. I want to see what the safety mechanisms are before I get into it. Not anywhere like reinforcement learning or deep RL or whatever the thing that, the hot thing is. I don't need millions of examples from this thing to, finally, I will get the courage to get into it. So that is what I mean by having a model of the world. And what is confusing is that it is actually possible to act on this world and be successful at it without building a model. And that is what often confuses people. That's what often gets billed as intelligence. And one example for this thing of acting in the world without building a model is called the old brain. In fact, if you look at the history of intelligence, old brain has been the driving force for creatures in this world for a long time. So the evolution of intelligence started almost 600 million years ago, started with sponges, jellyfish, flatworm fish, amphibians. We kept going, reptiles. All of these things were very, very successful. They existed in their niche, lived for a long time. So we started getting smarter things only much later. Birds and primates and humans became much more recent. So all this thing called old brain, those are species that existed in our world without having to build complicated models of the world. They were very, very successful. They had very sophisticated behavior that helped them survive in their niche. The old brain is really awesome. Let me show you some awesomeness of the old brain. So here is a worm. It's marching along on that tree twig. It's not falling off. It's very sophisticated behavior. Is it really thinking hard about how to go on that one? No. If it is thinking hard, it will be like, I don't want to get on that, right? So it's not really thinking hard. It has a reactive behavior, which somehow evolution figured out over a long, long time. It has a circuit in it which makes that behavior happen. And here is another example of a frog climbing a tree. It's very sophisticated behavior. It's not really thinking about it. It's just doing it. It has a circuit that was trained over evolutionary time scale to achieve that. And old brain was remarkably successful. If you might think, oh yeah, but they won't survive, etc. But if you look at the history, old brain is more successful than us. If you compress the history of dinosaurs to until now, dinosaurs appeared on Jan 1st. They went extinct on September 21st. We appeared only on December 31st. So dinosaurs survived more than us already. If you're just looking at survival as success. and they had just walnut-sized old brain. They did not have anything that we call intelligence and adaptability as the hallmarks of intelligence that we consider. So old brain is really awesome and confuses people about what intelligence is, but it has also many, many limitations. So some of the characteristics of the old brain are, one, it needs lots of training data. It generalizes very poorly. So the training is over evolutionary time scale. So evolution is the thing that is training these models up. It doesn't have a model of the world. And it gives rise to this illusion of intelligence. Most of the intelligence that we are ascribing to this, the intelligence is in us. We are anthropomorphizing many of the behavior as, oh wow, look, that looks so clever. It's actually just reactive circuits inside them. Here is an example of another sophisticated being, which has a behavior for going at these bugs. And in fact, a bug detector is trained on its retina, and it doesn't change its behavior even though it is not getting any nutrition. It would keep going at it. And so that's an example of old brain behavior that is not adaptive. And so old brain is nothing but a stimulus to response mapper. A stimulus comes in, there is some pattern matching happening inside, and it maps to a response. That's all old brain is doing. Yeah, you might go through lots of trouble to get to that circuit, but this is what old brain is doing. So AI today, I would argue that is more like the old brain. Why? Look at it. What we have is a trainable function. And what do we train it with? We have a list of stimuli accumulated. That's called the training data. Lots of it accumulated. And we have, for each training instance, we have the desired response also recorded. So that's a stimulus response. And we train it using backpropagation or reinforcement learning or evolutionary algorithms. And what comes out is a black box pattern recognizer with a very limited ability for imagination, reasoning, creativity, or thinking. But it does have a very good, fast stimulus to response mapping. Here is an example of another success. This is deep reinforcement learning playing the breakout game. And this was trained on millions of examples using reinforcement learning. And what you finally get is a pixel to action mapping. Input is pixels, output is actions. That is a network that is doing the mapping. But it is just like that frog. Here is the example. If I change the brightness 2%, I change the brightness 2%, it stops playing. Oops, let's see, can I play that? Somehow that video is not playing. Oh, it just stopped? Okay, all right. Yeah, so with 2% brightness, it misses. Somehow it's not coming up. But I have more examples of this. And you also know this famous paper, deep neural networks can be easily fooled. So these are networks trained on ImageNet for classifying things, but they can be easily fooled by showing these patterns. For example, that wavy thing is recognized as starfish. Many of these things that we call as noise is recognized as robin or cheetah, etc. Many of you are worried about robots taking over. Some of you are legitimately worried about how to survive this imminent robot apocalypse. I have an idea. So instead of wearing this T-shirt, you can wear this T-shirt with that pattern, and the robot will think you are a starfish, and you can escape. So that's the state of AI currently. It is more like the old brain. It requires lots of data to train, and the training is very task specific. You train for one thing, that circuit cannot do something else, even as simple as changing the brightness or changing the paddle, etc. So everything, most of these successes are like the old brain. So how do we build something like human level AI? You have to look at the structure that evolution came up with later. That is the new brain. And new brain is not just scaling up the old brain. It is structurally very different. It is not just accumulating a lot of old brain circuits and just hacking together stuff. The new brain is very different, and we need to understand the principles behind that. So we all have old brains inside us, but the new brain is put on top of it. It's a neocortex, that's a structure, and that's a structure that makes us adaptive and flexible, and almost all the things that ascribe as intelligence resides in this neocortical structure, and we need to understand the principles. So some of the characteristics of the new brain are, one, it requires much less training data. Just like, I will be able to get onto that contraption sometime without actually training on it. So that's an example of very low training data. High generalization. Learning a causal model of the world. As I was telling you, I am thinking about the consequences. What if I do this? What if my arm gets stuck? That's a causal model of the world. And so being able to build that and being able to query that. And also solves the common sense problem. And I would say common sense problem, which requires all these aspects to solve, is the holy grail of AI. Let me give you a demonstration of what this common sense problem is. So let me give you 2 sentences, and then I will ask you a question. So the first sentence is, John pounded a nail on the wall, and the second sentence is, Sally pounded a nail on the floor. And the question that I'm going to ask you is, in which case was the nail horizontal? Now, don't Google and look this up. It's you won't be able to find the answer there. So how did you? I don't care whether your answer is right or wrong, but how? Think about the process of getting the answer. You are actually imagining that situation. When I told you John pounded a nail on the wall, you imagined a John, you thought of a nail and a wall, maybe a hammer. All those things went through your mind. And so your language system is indexing into your knowledge about the world that is stored not in your language system. It is not a bunch of words. It's actually images about the world. It's your experience about interacting with the world that you are calling upon. And then you're reading the answer from that experience. So and this is a common sense answer, right? So this is not something you write down somewhere. This is something that you take for granted every day. These are the questions that you need to answer to pick up a cup and pour water from one cup to the other. These are the problems that you have to solve on a day-to-day basis, which I just converted those questions into language form. But this is something that you do on a day-to-day basis that forms common sense. And that's the crux of solving the AI problem, human-level AI problem. So one thing that you got from that is that you did use imagination and simulation. So you had to recreate that situation in some schematic form, not completely photorealistic, but in a schematic form, just enough to answer that question. So that is why generative models are important. So the rest of the talk, I'm going to be talking about 2 generative models. One is generative model for vision, and the other is generative model for dynamics. Generative models are important because it allows us to query a model of the world. So generative model is really a model of the world, and to solve common sense problem, you need to build generative models which are queryable. I need to be able to give it a sentence like John pounded a nail on the wall, and it should be able to imagine what that is. But that imagination is task dependent. It's not photorealistic. So you need to. So you have to think of it as the common sense reasoning requirement. That's a functional requirement that should drive the development of the generative model. So what kind of generative model? All generative models are not the same. So you will read a lot about generative models if you are reading deep learning literature or other probabilistic graphical models, etc. You will read a lot about generative models. All of these generative models are not the same. So let me give you some examples of the kind of questions that you need to ask when you read about a generative model. So some generative models are whole image generative models. They are modeling the whole picture. They don't try to factorize a picture into objects, background, etc. They don't care what is happening. All they care about is the picture photorealistic. So those kinds of generative models are not good enough for common sense reasoning because you can't ask it any questions. All it can do is generate a picture. So you need to have generative models which you can ask queries to. Some generative models, if you look in the literature, they have a query network which is separate from the generative model itself. And that query network is trained for a particular query. Just like the old brain is trained for a particular task, the query networks are, in some of the generative models, are trained for a particular query. If you want to ask the generative model a different question, you have to train it for that particular question. So, so these are and some of the generative models are just doing pixel-to-pixel regression. So they generate nice pictures, but they don't have any latent variables. They don't have any hierarchy of causes, etc. They are just modeling the pixel-level correlation. They can generate nice-looking pictures. They can do completion of pictures. So if you delete the lower half of the picture, it will fill it in. But funnily, it won't go the other way around. If you delete the upper half of the picture and ask it to fill it in the other way, it won't go in the other way because the regression is set up in a particular direction. That's an example of it not being able to answer queries that it was not structured to answer. So what kind of generative model is the brain? So our hypothesis is that the brain is a much more flexible generative model. It's a structured probabilistic model that you can query in many different ways. That you don't need an auxiliary network to query that brain, that generative model. You can ask it many different questions that you did not think about while training that generative model. So I will go through some examples of it as concrete instantiations. So the first example I'm going to talk about is a generative model for vision that we created quite a while ago, published only last year. So this was published in Science last year. This was the model that broke CAPTCHAs. So it fundamentally breaks the defense of text-based CAPTCHAs, and I'll tell you why it is important. And it's generative, and it trains with very little data. And it does inferences, most likely explanation. I'll explain what this means. So I mentioned that generative models need to be structured. They need to have rich structure. Where will this structure come from? We look at the brains. We look at actual neocortex data, actual cognitive science, neuroscience data to find out what are the inductive biases, what are the structural biases that you need to put into the model. And I won't be able to go through details of it, but I can give you a flavor. So these are, for example, some of the requirements that went into our model, like contour continuity via lateral connections, contour and surface factorization, border ownership coding, top-down object-based attention, inference dynamics. These are all properties of visual system that we know. There is existing data for these properties of the visual system. Neuroscience researchers have actually gone and really probed the brain and found out what exactly is happening there. So we took it as that we have to build a model that incorporates many of these constraints. I can just give you two examples from this one. What is factorized representation of contours and surfaces bias? So here is a rainbow banana. You have never seen a rainbow banana before, but you can recognize it. And that's because you have a separate representation of the surfaces of the banana, of the appearance of the banana, compared to the shape of the banana. So I can show you a chair made of ice. Even if you have never seen that before, you can still recognize it. That's because they are coded separately. Another one is object-based top-down attention. So you can separate out overlapping objects. They are occupying the same space, but you can separate them out. This is a capability that human brains have. Being able to do that imposes certain constraints on the model. All models are not able to do that. So these are the kind of constraints that we make sure that our model can deal with. Cracking CAPTCHAs. So why are CAPTCHAs important? So the reason why CAPTCHAs are important is that they show examples of new brain generalization. They are a very good example of a problem that looks simple, but it's actually very complex. You can get all the richness of AI problem in the CAPTCHA problem. I can, these are all examples of CAPTCHAs that people in this room will be able to solve, but I did not give you millions of training examples from each of these CAPTCHAs. You just can solve them based on your experience with the world. In fact, even a single letter A can be rendered in so many different ways. Current deep neural networks will not be able to deal with all those variations. In fact, one of the brilliant philosophers in AI, Douglas Hofstadter once mentioned that the central problem in AI is just recognize the letter A. That's it. If you can recognize the letter A in all situations, you have solved AI. We are far from that. So that's why. So this is the reason why CAPTCHAs are important, and that's the reason why we picked up CAPTCHA as a problem to attack, because solving it the right way with very little training data and showing strong generalization shows the capabilities of the system and the important problems that need to be solved. So let me go into some of the model details. So I'll go over this quickly. You can read the details in the paper. So at the very high level, it has a contour hierarchy and a surface model. And the contour hierarchy and the surface model interacts in a very particular way. So you can think of a surface model as nodes in a graphical model, and they are just model. The surface model is saying, I expect surface to vary smoothly. So if I see a red pixel here, the neighbor is also likely to be red. If I am on a smooth surface, the curvature is going to vary slowly. This is what the surface model is saying, except when there is contours. So the contour model is telling the surface model, expect smoothness when there is no contour in between. So that's the interaction between the contour model and the surface model. So the contour nodes are the ones sitting on the top. They are telling the surface model that we can expect continuity when there is no contour. So, and during inference, of course, these work together. The presence of contours and the presence of smoothness of the surfaces both need to be inferred. But this is how they interact. And if you sample from a particular instantiation of contours from the top, you can generate all these surface variations of a cube. The contour hierarchy is it's a hierarchy of features going from very simple line detectors at the lower level to more complex contours and corners and object parts at the top level. And this is completely learned from data. And many of the structural aspects are similar to convolutional neural networks, if you're familiar with that. There are two differences. One, this is a generative model. It is not just doing pattern recognition in the feed-forward pathway. It's a generative model, so it can do reasoning in both directions. The second thing is it has lateral connections. So let me explain what these lateral connections are. So lateral connections are something that constrains how things vary in two different pools. So if I have a pool here which is telling me that lines can be anywhere in this location, and if there's another pool here which is telling me the lines can be anywhere here, there needs to be something that constrains their variation. This is what enforces contour continuity. So if you sample from a corner without the laterals, you will get jaggy corners, and if you have with lateral connections, you will get smooth variations. And you can have this parameter tuned so that you can generate different variations of this A just by changing this one parameter. And inference in this model, so this model, after having learned, is, you can think of it as trying to explain a whole scene. So give it an input image, it will try to come up with an explanation for the whole scene, saying that, okay, these are the objects, these are the pixels corresponding to this object, this is the background, etc. And to do that, it does message passing in the model. Message passing is a technique to do inference in a probabilistic graphical model. There are many other techniques, but message passing is fast, just like our brain is fast. Although it is approximate, it is a technique that can come up with results at the same speed as our brain is coming up with results. So that's why we focus on message passing as the inference mechanism. So a first forward pass can come up with a set of hypotheses on what are the objects present in the image. And then the backward pass is focused on the top hypothesis, and a backward pass can generate explanation. So if I am focusing on A, it will segment out the A. If I am focusing on O, it will segment out the O. And it can also hallucinate things in between. There is a V that exists. If you think of that, the pieces of the V that exists, it is there, but it's a hallucination because that V can be explained away by the presence of other things. And that is resolved through parsing, which is what it's explaining away. And the technical term is finding the map solution. So you're trying to find the maximum a posteriori solution for the query, and that is what comes up with the best explanation for the scene. Let me skip this one. So let me go to what it can do. So it can parse CAPTCHAs, as I mentioned, without. Important to remember that it is not trained on these CAPTCHAs. We are training it on just letters. It doesn't even see the CAPTCHA string, but it can parse all of them and generalizes to different deformations. And here is another family of CAPTCHAs it can solve. And here is in contrast to deep neural network. We did a study on one-to-one study on how, comparing with deep neural network. You can train deep neural network to solve a particular CAPTCHA. So this was on reCAPTCHA style CAPTCHAs. So our network took about 260 images, just clean fonts, to get to the performance that we wanted, about 90% performance. And deep neural network took about 500,000 examples to get there. But that is not the only problem. Now, suppose after training, I take this CAPTCHA and just, I'm not changing anything other than just changing the spacing of the letters. So this is what happens. Our model stays constant. In fact, it actually becomes a bit easier because when they are not, the letters are not interacting, it's easier to separate them out. But deep neural network, it just goes down in accuracy. So even after having seen millions of examples, of course, people who know how deep neural network will say, of course, you can't expect it because it didn't see that kinds of data. But that's exactly the point. That is, humans do not need to see those kinds of data to be able to generalize. Also, one thing I want to emphasize is that RCN, that's what we call our model, recursive cortical network. It's a joint model, a single integrated system for multiple different problems. It can do classification, it does parsing of a scene, it does generation and denoising, it can do occlusion reasoning. And when we compare in our paper, we are comparing our system with systems that are specifically built for each of those purposes. So here is us comparing in classification. This is on MNIST data, but variations of MNIST data with occlusions and noise, etc., and showing that we are actually performing very well compared to deep neural networks. And there we are comparing with CNN. And reconstruction and denoising, it's the same model. We are comparing with variational autoencoders there. And in occlusion reasoning, so the occlusion reasoning is very interesting. So here you can see that the input features for both these interpretations are exactly the same. The only thing that I have changed is where those clouds were placed. Your interpretation of one of those images is N and the other image is S, but the input features of the objects are exactly the same. It's only the occlusion pattern that has changed. And deep neural networks have big trouble with that. They cannot reason about these occlusions very well. Our system can reason about occlusions very well, and it can also generate data, conditional generation of data without any input. So there also we can compare with VAEs. In addition to that, we also tried on 2 standard benchmarks for real-world text recognition. This is IGDA data and the Street View text data. And on both those things, we were able to beat deep neural networks with much less training data, almost 300 times fewer training data. This is the picture level representation of that. So if you take 1 pixel as a training data point, this is what the training data for the Google system looks like. And our data is not visible on that picture. So that shows the difference in scale required for these systems. And the next thing I want to talk about is generative model for dynamics. So that was generative model for vision. And so that is, if there are objects in a scene, how do you interpret that scene? And next, I'm talking about generative model for dynamics, and that is what models interactions between objects in a scene. Internally, we think about all these things as the same thing. We are internally, we are thinking of it as part of the same model that we are building with a cognitive architecture, etc. But of course, when we publish something, we have to talk about one piece of it at a time. In the future, hopefully in the near future, we hope to bring out some of these papers that combine this into one cognitive architecture. So let me go ahead with the generative model for dynamics. So you've seen the deep reinforcement learning technique playing games. But as I mentioned, it learns to play these games in a model-free way. It is learning a lookup table, a brittle mapping from pixels to actions, and yes, it can play human level at that particular training set, but it doesn't generalize. So here, so this is on the left-hand side is the success story. That is, this is deep Q learning playing the game very well. And the next one is if you move the paddle just 3 pixels up. So the only change between that first image and the second image is that the paddle was moved 3 pixels up. Okay, let me try that again. And then it starts missing the ball quite often. So that's what I mean by it being very, very brittle. So moving the, you might not even have recognized that the paddle moved 3 pixels up, but this system fails completely on those kinds of transformations. So we published a paper in ICML last year about our approach to solve this the game learning problem compared to deep reinforcement learning. And our approach is called Schema Networks. And what's different in Schema Networks is that we are trying to build a causal model of what is happening in the game. We want to understand that there are objects, there are interactions between objects. We want to understand what the effect of interactions would be. So those are the things that go into the model. And finally, the end result is a graphical model that is learned, and you can call it an object-oriented MDP, a Markov decision process, and it has entity-based representations. Rather than thinking of the world as just pixels, it thinks of the world as having objects and interactions between them and having cause and effect. So the result of doing that is that we can deal with these variations. So in the paper, we talk about the different kinds of perturbations that we can do to the game. So we can do things like moving the paddle up by a few pixels. You can insert a wall in between. You can change the colors of the reward. You can move the reward around every frame. So there are so many. You can think of an infinite number of perturbations that humans will be able to deal with very well. In the paper, we tested only on 6 of them, but it will generalize to many of others too. So let me show you some examples of this. So this is on your right is DeepMind's Q learning, and so that's, I think, just the normal game. And this is So this is just the training set. Both of them play the training set very well. And the next one is 2% brighter. Okay, let me play that again. That is 2% brighter. Okay, it doesn't play the full video, but it misses quite often, or in the 2% brighter case. And Vicarious Schema Networks, 2% brighter, it doesn't register at all. It's no problem. So let's look at the offset paddle. So this is what happens with Vicarious Schema Networks with offset paddle. It can play the game, no problem. And this is what happens with offset paddle for DeepMind system. Our system can play with multiple balls, no problem. So it'll just keep hitting the ball back. So this is with a wall introduced in between. So this is a wall which comes in between. Since the Q-learning model does not know anything about what walls are, what obstructions are, etc., it will just keep hitting back at the same wall, not earning any points. And this is what happens when, without any training, the wall is introduced into the system. Our model just plants around the wall. It hits around the wall to keep getting rewards. You can introduce multiple walls all flying through. That is fine. It will think about what to do in that and hit properly in that to avoid all those walls. In fact, this is a picture of what is happening inside the system during the, so this is showing how the system thinks. So all the white pixels are in its imagination. So it plays forward multiple scenarios, just like I was talking about playing forward the different scenarios on getting into that contraption. So it plays forward multiple scenarios and then picks an action based on what's the best scenario. So one takeaway message from all this is that we need to be careful about what human level performance means. On one hand, the Adadi playing deep reinforcement learning agents are human level. That was the top, title of the paper, the human level game playing. But as I was shown here, that's not a, in a meaningful way, it is not human level, because humans can play that game even if you make these small perturbations, whereas that other human level agent cannot play. So this is a problem in the way we are measuring human level performance or declaring human level performance. What we should be measuring for is human level robustness rather than human level performance on a single data point. Because if it is just a single data point, you can solve it the old brain way. All you need is tons and tons of data. And so with enough computing power and enough data, any particular instance of the problem can be solved well. But that solution does not give you any hint on what's the right way to go to build human level intelligence. In fact, it can just throw you completely in the wrong direction. You can think that, oh, I can just scale this up. I just need more GPUs and more data and more engineers, and I will get there. But it can be completely in the wrong direction. And the last few minutes, I want to talk about going from neuroscience back to, from the graphical model back to neuroscience. So this is one of the topics that I am very interested in. It's a side project for Vicarious because Vicarious is all about build models based on neuroscience and cognitive science, not necessarily explain neuroscience data. But I personally am very interested in also understanding the human brain and explaining circuits of the human brain based on the models that we build. So the path looks like this. As I mentioned, you build models which are specified in the language of probabilistic graphical models. That's how we actually build systems. But you can then go back from that probabilistic graphical model to see how they can be implemented in the brain. And then you can ask the question, can it start explaining some phenomena from the brain? Can it explain some circuits from the brain, etc.? So we have 2 recent papers about this in a conference. You can look it up on our website. The answer is yes, you can go back from our model and start explaining some phenomena that happen in the cortex. So for those who are not familiar, the cortical circuit has some very systematic structure. So a piece of the cortex is organized roughly into 6 layers of cells, and they have a very, very stereotypical pattern of interconnection. Inputs go into layer 4 of the cortical sheet, and outputs go out from layer 5, feed-forward connections go out from layer 2, 3, there are long-range lateral connections in layer 2, 3, and layer 5, 6, etc. So you can think of the process is basically how can you explain those circuits based on the computational requirements of the model that you have already built. It won't be too much of a surprise because the model that you're building is based on hints from from neuroscience. So it is expected that you'll be able to explain that, but it has to fill in a lot more details. And I did this once a long time ago in 2009. We wrote a paper. I wrote a paper with Jeff Hawkins on how to do this. This was based on the HTM model at that time. The RCN model is a much more improved version, so it should be able to go back and explain more phenomena. So I can explain what this instantiation is at a very high level. So you can think of a cortical column as a binary random variable. So think of each cortical column as representing a concept. So at the lowest level of the visual hierarchy, a concept would be something like the presence of an edge or presence of a color, etc. So that would be a binary random variable. Each cortical column is just signaling whether that feature is present or not. So the output of the cortical column is about what's the likelihood of that feature being present. And every layer in the cortex is organized like that. Every level of the hierarchy. Each cortical column is just signaling the presence and absence of a concept or a feature. But there are so many things to talk about this particular feature. I'm talking about a vertical line. I need to understand how does it occur in the context of vertical lines or horizontal lines nearby. So those are the lateral connections of that particular feature. I need to understand how does it participate in features which are downstream. So that's how, how does a corner unfold into child features? So that's how, that's the participation of that particular concept in downstream features. There needs to be neurons that code how it will send messages up in the hierarchy. There needs to be neurons that tell how does it unfold in time. How do you transition this particular feature in, how does it look when the time unfolds. So these are all the different aspects that need to be talked about for that particular feature, and those are the different layers in the cortex. So as I mentioned, a cortical layer has, a cortical sheet has roughly 6 layers with more micro divisions. So these divisions are the participation of that one concept in different roles. And the roles that I've denoted here are how they participate in lateral connections, how they compute the belief. Belief is something that needs to take into account not only bottom-up evidence at the current instance, but also influence from the past, influence from the priors, etc. Feedback computation. So all these things need to be done for that particular feature, and that's how, and those are the roles for the different cortical layers. So so in this paper, we also talk about how a structure in the cortex, so this is not part of the cortex, it's a subcortical structure called the thalamus, and how thalamus and the cortex works together for creating something called this explaining away mechanism. It's not something cortex alone can do because it needs some extra supporting circuits. Explaining away is the example that I showed in my previous slide, where that hallucinated V was explained away by the presence of an A and a K. So that's the process of explaining. You are explaining some evidences. That evidence, although that evidence is present, you are saying that that evidence can be explained by other things. So that needs a specific form of computation, and when we looked at it, it fits the circuits that are going through the thalamus. So it's like solving a puzzle. Like you look at the computation and see which cortical structure would fit that. And similarly for the interaction between the surfaces and the contours, our model can make very specific predictions about how the columns corresponding to surfaces, which are actually called blobs in neurons, in neuroscience. Those are the columns that represent surfaces, and interblobs, which are the columns that represent contours, how they interact. We can make very specific predictions about that from our circuit. We can also explain some visual illusions. So this is a classic illusion called neon color spreading. If it shows up properly, you should be able to see a cyan-colored disk. That's the illusion that you should be able to see. I don't know whether you're able to see from here. I can definitely see it on my computer. So if it is rendered correctly, people see a cyan-colored disk, although that disk is not there. And you will also see the edges of the disk as if there are edges there. Those edges are not there. So if you're seeing a complete disk, the edges of the disk actually doesn't exist. So your brain is hallucinating. So let me mark what I mean here. So if you are actually seeing a boundary there, even a faint boundary, that doesn't exist. If you look in the image, it doesn't exist. Your brain is actually creating it. And the color that you think that is internal there, if it is a light cyan color, no, it's actually, in the image, it is pure white. It's just same as the background. Your brain is hallucinating that color. So why is the brain doing this? Because that is the best explanation it can come up with for that picture. So your brain is always trying to, as I explained before, our model and the brain is trying to explain a scene. And as long as it can fit an explanation onto the scene, it will make things there that are not there in the picture. It will create things because that is the best way to explain that image. So these illusions we should be able to explain using our model. And indeed, we can explain this illusion. So if you give a picture like this as input to our model, it will hallucinate those circles, the circle that doesn't exist, and it will also fill in the color because of this interaction between the contours and surfaces in our model. Once the contour is hallucinated, the color is filled in uniformly inside the interior of the object. So it will hallucinate the contour. So those are the blue stars that I have drawn there. That's a hallucination of the contour, and it will actually fill in the surface. I don't have a good picture for it. Okay, so to conclude, so the characteristics of the new brain that we are emphasizing in our research are: 1, low training data, high generalization, learning a causal model of the world, and solving the common sense problem. And I hope I have showed you some examples of how we are going about it and some concrete results. And where are we applying this? We are applying this in robotics. And robotics is a place where all these things actually need to come together if they are going to be effective in unstructured environments. Having the manipulation ability and common sense of a 3-year-old child, that would be a very fantastic achievement. We don't need to, it doesn't need to play chess or Go or anything like that, but being able to understand and manipulate the world like a 3-year-old child, that would be crowning success for AI. So our robots are currently able to do some very simple things like assembling toys, picking up objects and putting them into boxes, etc. And our goal is to automate many tasks on the assembly line. That's how we are going to enter the market. So this is a picture of assembly line from the 1900s, and this is a picture of assembly line from 2000s. Nothing much has changed. It's all still people standing in a line and assembling objects, except for the color picture. It's all the same. So we hope that we can make 2030s. It will be more of this work will be done by robots. That's our goal, and we are building an AI layer so that it can be applied on multiple robotic hardware platforms and can be applied in different verticals in the manufacturing industry. For more information, you can always go to our website. We have our research papers on there. You can follow us on Twitter, Vicarious AI. You can email me if you have questions about the presentation. And you can also follow me on Twitter. I have the coolest handle, which is Dileep Learning. So thank you.
Okay, thanks a lot for a really inspiring keynote. We're doing the question game again. So, who is Michael van Elk? Okay, Michael is asking, would you say your approach is similar to Hinton's capsule networks?
Oh, yes. Yes, there are many similarities in Hinton's capsule networks and our thinking. So I don't know how many of you are familiar with Hinton's capsule networks. So this was a paper Hinton published actually just just a few weeks after our paper came out. Some of the assumptions that they made are similar to the assumptions that we made, which is one, having object-centric representations, being able to explain away the evidence of an object based on the presence of other objects, giving importance to parsing a scene as opposed to just classifying one character at a time. These are all things that they emphasized in their paper as well. And what are the differences? One, they need tons more training data to train compared to our network. Their network, as it exists now, also needs to know the number of objects in the scene. So if I want to train an object with a system for parsing 2 objects in the scene, it needs to know, okay, the scene has only 2 objects. So it's not flexible enough to handle unknown number of objects in the scene. And it requires so their system to go from 1 object scene to 2 object scene, it required almost going from 60,000 training example, which is the MNIST, to 1 million training examples. So that factored representation of objects is not something that they handle well, but the assumptions that they are making are very similar to ours.
Okay, Fabian Klopfer, over there. Compared to Schmidt-Huber's world model, how does the internal or latent representation look like for different tasks?
So the difference in our world model is that we are not trying to make image-level photorealistic predictions. Our model is about having structured internal representations that you can query in many different ways. I don't think Schmidt-Huber's model is tested in that setting. It is mostly tested in the setting of here is the large amount of training data, and the querying is also in the same distribution, where you don't take a very different test distribution compared to the training distribution.
Andres Suarez, how do scheme networks perform with more radical changes that are still trivial to humans, like upside-down brick game?
I don't think it will do well with upside-down. So I didn't want to imply that will do as well as humans on all transformations. No, we still have quite a long way to go. And upside-down transformation, I'm not so sure how well humans will adapt with a little bit of practice. They definitely won't need a lot of data. I don't think schema networks as it exists currently will do well on that transformation. So yeah, there are lots of transformations that you can do to that game that humans will do well. Schema networks will still not do well.
Jakub Bares, somewhere up there. How should we encode the knowledge learned by models simulating the human brain? Vectors or ontologies with logic?
So figuring out the representation is one of the biggest problems. So we use the framework of probabilistic graphical models. And many of the things that you mentioned do fit into that framework. You can build ontologies there. But graphical models itself is restricting. They don't capture all the things that we need to handle. So it would be probabilistic graphical models combined with programs. So you can think of it as, some people call this probabilistic programming, but you can expand the model class of probabilistic graphical models using programs as an additional thing. So programs combined with probabilistic models. That's the representation language that we use.
Gustav Surek. Gustav, where are you? Oh, righty. It seems that quite some background knowledge is put into the structure of your model for each of the tasks. Is it a fair comparison with deep neural networks then? Aren't they, in a sense, more general without any knowledge about the objects and notion of their interaction?
Oh, yeah. Yes, deep neural networks are more general in the sense that all brain was more general. So you can have one algorithm called evolution, and you can give it lots of examples and create a circuit for that particular purpose. So yeah, if your goal is to make very few assumptions, and try to solve AGI with that, then I would say don't even try, because that is not, because it will take an evolutionary time scale to be able to get there. So we are attacking it from the point of view of what are the right set of assumptions. You don't want to make too many assumptions, then that becomes too specific. What are the right set of inductive biases, the minimal set that you want to build into your system so that learning becomes much faster, inference is easier, etc., etc. So some of the comparisons are not fair in this, as you say, if you're trying to say they should be able to make the same assumption, then it's not fair. But if you go back to the bias variance dilemma paper, if you're not willing to put biases in your model, then there is, you can't do much. The only solution is to have infinite data which is available only theoretically. It's not practically available. So that should be, I had one more thought related to that. Hopefully it will come back.
Okay. Andres Suarez strikes again. Doesn't the old brain contain a hard-coded model of the world, hence worms don't have to think about their actions?
Can you repeat that?
Doesn't the old brain contain a hard-coded model of the world, hence worms don't have to think about their actions?
Yeah, so this is, it's not a model of the world that they have, it is amortized inference that they have. So you can think of a model of the world and a question on the model of the world. So you can, the answer to that question, you can make a circuit that answers that question very fast, but only that question. So that is called amortized inference, right? So it's like you take a model and just the answering of one question, you do all the computations upfront so that the lookup is very fast. This is what neural networks is doing, right? It's doing amortized inference. So the worm has an amortized inference circuit for a particular task. So that is correct. The important part is that you cannot amortize for all the kinds of things that you want to think about. So you need to have a system that can do amortized inference on one side of the thing. So we do use neural networks also in our system. So it is compatible with neural networks, the whole thing. So you can amortize some parts of the questions, but you cannot, that amortized inference is not flexible enough for thinking about things in a compositional way.
Okay, and then the final one from Jeff Thompson. This now is a Silicon Valley style one. Really? You won't enter the market until the 2030s?
Oh, no. So that was more a vision picture in saying that we hope in 2030s factories will be like that. No, we are in advanced prototyping stage, and hopefully our products should be in pilot stage in the next couple of months. And going for deployment definitely in months time frame rather than years time frame. So that's the status.
Okay, as I said, 122 million registered on the crunch base. I'm sure if you walk up with at about the same amount, they would consider a Series E, F. Where are we?
We are at Series C.
Okay. Let's call it 120 on C if anyone's interested. Okay, thanks a lot, Dileep.
Thank you.